Kaluza had the idea of unifying gravity with electromagnetism, which at the time were the two forces that were best understood. The strong and weak nuclear forces weren't very well understood. So it was natural to try and ask, is there a unified description of gravity and electromagnetism? And he had a wonderful idea. He said, let's take the four coordinates of Einstein's space-time and add a fifth coordinate. Let's call it y. Call that Zm. So you've got a five-dimensional space-time with a metric gmn dzm dzn. And I'm going to put a hat on the metric to remind us that that's the five-dimensional metric. And he said, let's take Einstein's Lagrangian, which I'm going to adopt a convention where kappa squared is 8 pi g. Erase. So the Einstein Lagrangian is this. And Kaluza said, now let's make a 4 plus 1 split. And write the 5 by 5 matrix in 4 plus 1 split. So in this corner, we've got g hat mu nu. In this corner, we've got g hat mu. Now we'll call these mu equals 0, 1, 2, 3. So the fifth coordinate will be 4. G hat 4 mu, g hat 4, 4. Now we make a change of variable. And you'll see why in a minute this is a useful one. So all we've done is a change of variable. We had, this is a symmetric matrix, so we had a 4 by 4 matrix, one vector, one scalar, and we've swapped it for another 4 by 4 matrix, one vector, one scalar. Now, to begin with, you would expect fields to depend on both x and y. But Kaluza's idea, and I'll tell you how Klein handle things in a moment, but Kaluza's idea was to ignore the y dependence. That was just a postulate. And we'll see what happens if you relax that in just a minute. So we look at this 5-dimensional world, and the idea is that G mu nu of x, A mu of x, and phi of x are now fields living in our 4-dimensional world. And Kaluza said we're going to identify this with the Einstein metric. So this is a 4x4 metric that we're familiar with already. But the new ingredient is we're going to identify this with Maxwell's field. And then this is a new field, which is sometimes called the dilaton, and which at the time was considered an embarrassment because there were no scalar fields known. And today, with the exception of the Higgs, there aren't any scalar fields known either. On the other hand, this is a very simple version of the kinds of higher dimensional theories we now look at. So let's not worry about whether the dilaton is a real field or not for the moment. This was all before quantum field theory, but nowadays we'd call this a spin 2 graviton, a spin 1 photon, and a spin 0 dilaton. Now, it's not enough just to say I'm going to call that the Maxwell field. If I'm going to unify Maxwell's theory with Einstein's theory, I have to show that we get Maxwell's equation, that it obeys Maxwell's equation. And this is the miracle of Kaluza's idea. When we plug this 5-dimensional metric into the 5-dimensional Lagrangian, and this is the 5-dimensional one with the hats on it, we get the 4-dimensional Lagrangian plus other stuff. What do we get? We get R minus 1/4 phi F mu nu, F mu nu, minus 1/6 kappa squared, phi squared, d mu phi, d mu phi. Where F mu nu is d mu a nu minus d mu a nu. Now, before we talk about Maxwell, let me say a word about this 1/phi squared. I was asked this morning, what does it mean to have the inverse of a field? Because we encountered a 1/phi also in the Brand-Sticky formulation yesterday, ω/phi d phi squared. But this is just a choice of parameterization. And we can, it's convenient to define phi as e to the alpha kappa sigma. Let me leave alpha arbitrary for a moment. We'll fix it in a moment. So d mu phi is alpha kappa d mu sigma e to the alpha kappa sigma. If we plug this in here, we get minus 1/4 e to the alpha kappa sigma f mu nu minus alpha squared over 6 kappa squared e to the minus 2 alpha kappa sigma d mu sigma d mu sigma. Now we want this to look like, if we want this to look like a canonical scalar field Lagrangian, this has to be minus 1/2. So we choose alpha squared equals 3. And we end up with so this is the canonical Maxwell Lagrangian with some interactions with the scalar field. If we expand out the exponential, the first term is just Maxwell's term. And then there's some extra terms which tell you that the scalar field sigma is interacting with the photon field. And similarly, this is a self-interacting scalar field. So by choosing the right variables, we can get rid of the 1/5s if you don't like them. But you can put them back if you like, because this is what's really going on. But the miracle, leaving aside the scalar field for a moment, is that the Maxwell Lagrangian has come for free. We didn't postulate that the Maxwell Lagrangian was f mu nu, f mu nu. It came out of Einstein's equations. So the Maxwell's theory, f mu nu, f mu nu, is a consequence of Einstein's theory, if you're willing to buy the idea of the fifth dimension. Now, you can ask about gauge invariance. Maxwell's theory has a gauge invariance. But we started with a 5-dimensional general covariance. So this is psi m, which is psi mu psi 4. This implies a 4-dimensional general covariance with parameter psi mu of x. But plus, there's an extra bonus, gauge invariance with parameter psi 4 of x. This is what we normally call, so the gauge invariance is delta a mu of x is d mu psi 4 of x. So the gauge parameter of Maxwell's theory is just the 5th component of the general covariant parameter of Einstein's theory. And Maxwell's gauge invariance is just coming from general covariance in an extra dimension. Now, there's a couple of objections one could raise at this point. First is, if there's really a fifth dimension, which people raised at the time, if there's really a fifth dimension, why haven't we seen it? And that's one question. And another question is, this seems rather ad hoc on the assumption. And these problems were addressed by Oscar Klein. By the way, Kaluza sent his paper to Einstein. He sent his paper to the journal, and the journal sent it to Einstein to referee. And Einstein sat on it till 1921, and eventually decided it wasn't such a bad idea after all. And he apologized to Kaluza and said, I've now recommended publication. And he, in fact, wrote some papers on the idea himself. But in 1921, Oscar Klein, I'll tell you another story about Kaluza. He belonged to that school of thought that believed that you could derive everything from pure reason without resort to empirical test. And according to his son, who is a mathematician in Germany, he put this to the test by learning to swim from the textbook. So he would lie on the living room couch with the book in one hand, practice the strokes with the other. And then he walked to the nearest lake and swam from one side to the next. I find it easier to believe in 5 dimensions than I do in the truth of that particular story. Anyway, Klein came along and said, well, why are you assuming things are independent of y, and why haven't we seen the fifth dimension? And his answer was, the x-coordinates go from plus infinity to minus infinity. But let's assume the y-coordinate is periodic. So you set out in the fifth dimension, you come back to where you started from. That's a different topology from the other 4. Now you can Fourier expand all your fields. And Kaluza's theory is just the first term in the expansion. So there are really infinitely many fields, of which the graviton, the photon, and the dilaton are just the n equals 0 modes. But you have an infinite tower of other fields, and they have charges E sub n and masses m sub n. So they're quantized. And the masses are go like 1 over r in appropriate units. So the smaller the circle, the fifth dimension, the bigger the masses. And if you take E to be the charge on the electron, so how's the formula go? This also depends on the radius. I forget the Newton's constant. But if you take the electric charge with the charge on the electron, R is very small, 10 to the minus 33. centimeters. So that would explain why we haven't seen the fifth dimension. You would need to probe very, very short distances before you became aware of these heavy states. And that's the situation, roughly, that we face today with extra dimensions. If they're small enough, we wouldn't detect them directly. And we wouldn't see the heavy states unless we had accelerators that could probe very short distances. Now, there are variations on this theme where the radius is not the Planck radius, but something smaller. But whether you believe those theories or not is up to you. If you did, you might expect to see these states at the LHC, which they're also microscopic black holes as well. These massive Kaluza-Klein states can be interpreted as extremal black holes. But my own view is that if there are extra dimensions, they're very small, and we are not going to see them directly, but I may be wrong. Yeah?
So why, if we have quantization, so if the y dimension is looped onto itself, why does it also imply quantization of the graviton? And
why does it?
Why does it also imply the quantization that you mentioned? Of the
No, sorry, when I said quantized, it implies that the electric charge is quantized, which is also another virtue, because at the time there was no, this was the first attempt to explain why electric charge is quantized. Now, there's another argument for quantization of electric charge due to Dirac involving magnetic monopoles. If there's a magnetic monopole with charge G, the electric charge has to be quantized in terms of 1 over G. Interestingly enough, in M theory, these two different explanations for quantization, the Dirac quantization and the Kaluza-Klein quantization, turn out to be dual descriptions of the same thing. So you don't have two explanations, you really only have one. But that's another story. So this was the first attempt to invoke extra dimensions, and it had the nice feature that Maxwell's theory comes for free. It fell out of favor for many years. Einstein worked on it for a while and gave up on it. Pauli almost discovered Yang-Mills theories in the 1930s because he said, let's try this trick not with a circle, but with a sphere. And with a sphere, you see, the reason you're getting Maxwell's theory is that the circle has a U1 symmetry. If you have a sphere, you have an SO3 or SON symmetry, which is non-abelian. So instead of getting an abelian Maxwell theory, if you did things right, you'd get a non-abelian Yang-Mills theory. But Pauli didn't quite get it right. So he almost discovered Yang-Mills theories in the 1930s, as did Klein. But it wasn't sorted out properly until Yang and Mills did it in the 1950s. So that was the diversion into extra dimensions. Now we come back to Earth and 4 dimensions. And we continue with our quest to incorporate fermions into the story. Are there any questions on this?
It's possible, I mean, if you consider sphere, then you get the dynamic view?
Yes, you get Yang-Mills theory. If your extra dimensions are, you see, it's technically speaking the isometry group of the extra dimensions. is the Yang-Mills gauge group. So if you have a sphere where the isometry group is SON plus 1, then you would get a Yang-Mills gauge group with that group. Now you could ask, as Witten did in 1980, can you get the SU3 cross SU2 cross U1 of the standard model this way? And curiously enough, the minimum number of dimensions you need to do that is 11, which happens to be the maximum number of dimensions permitted by supersymmetry. So there was a hope that maybe 11-dimensional supergravity compactified on the right manifold would give you the standard model. Alas, it didn't work, because although you get the right gauge fields, you don't get the right quarks and leptons. In particular, the standard model, the quarks and leptons are chiral. The left-handed fields behave differently from the right-handed fields. And that was difficult to incorporate into the 11-dimensional supergravity. So it was an interesting exercise, but no cigar. Nowadays, we still have hope that 11 dimensions may explain the standard model, but it's not with the supergravity, but with M theory, of which supergravity is, if you like, the low energy limit. And there are ways of compactifying M theory that circumvent the no-go theorems and allow you to get chiral fermions. So the ingredients are there. You can get gauge fields, you can get chiral fermions, you can get Higgs bosons and all the rest of it. But the problem is there are millions of ways of compactifying the 7 dimensions of M theory. And we don't know which, if any of them, is the right one. And we haven't even tabulated them all. So the right one may be one that we haven't found yet. So, any other questions? Yeah?
Sorry, what exactly is the significance of the sigma?
The sigma field.
Yeah, sigma.
The dilaton. Yes. Well, we don't know, because in nature, no one has seen such a field.
Right, so at this point, we haven't identified that sigma field with anything.
With anything physical,
Right.
no.
It's just-
No. And all our favorite unified theories have a multitude of scalar fields, which, again, if they remain massless, would be bad news, because they would spoil the experimental tests that we've been discussing, for the same reason that Brans-Dicke doesn't work. However, if they get a mass, which they can do with the right compactifications, then it wouldn't contradict the experimental tests, but it still leaves you with the question, well, where are the massive scalar fields? Should we be seeing them in the laboratory, or are they too heavy? And there's lots of different models. And we may mention this, it's probably going to be tomorrow now before we get on to cosmology. But the paradigm theory for the history of the universe is inflation. It's believed shortly after the Big Bang, the universe underwent an exponential expansion, which fits the data very well, but on theoretical grounds, it's a bit shaky, because we're still not sure what drove the inflation. And everyone's favorite candidate is something called the inflaton, which is a scalar field like this one. But to have a field which is invented for no other purpose than to be the inflaton is not very satisfactory. We'd like to think that it was part of some more consistent framework. And so the arguments over what the inflaton is continue. But to answer your question, there's another place where a scalar field like this might be.
Well, Randall
Physical.
Sundrum theory, I've seen it.
Hmm?
I've seen a dilaton in Randall Sundrum theory.
Yes, there's dilatomes in their theory too, that's right. So there's no shortage of scalars in theories. It's in experiment that they're in short supply. Okay. We started talking about Vierbeins, and the problem is that fermions transform according to the spinor representations of the Lorentz group, and they don't fit into the framework of ordinary general relativity that we've been doing so far. We have to invoke these Vierbeins. But we need to say a little bit more about the Lorentz group than we've said so far. And this is in Weinberg, page 58. Now, you remember, so let's just remind ourselves about flat space to begin with. A Lorentz transformation is one for which x goes to lambda mu nu x nu, and lambda was any matrix that satisfied this equation. It leaves invariant the Minkowski metric. Now, a general field which I'm going to call psi alpha, and I'm not going to specify at the moment what alpha is, transforms as omega of lambda alpha beta psi beta. And omega obeys the group rule that omega of lambda 1 times omega of lambda 2 is omega of lambda 1 lambda 2. And this is what we call a representation of the Lorentz group. Now, there are different kinds of representations. Let's look at some examples. A vector representation is one where omega is lambda itself. And a tensor this index alpha, this abstract index alpha, stands now for two indices, CD, AB, and omega is lambda CA, lambda DB. That's how a rank 2 tensor would transform. But these are not the, and you can do rank 3 tensors, rank 4 tensors in the obvious way. But these are not the only representations of the Lorentz group. There are also what are called spinor representations. Which I abbreviate as REPs. And to understand these, let's first consider infinitesimal transformations. So we write lambda AB as the unit matrix plus delta omega AB, where delta omega is infinitesimal. And if we plug that in to our equation, we have eta AB times delta AC plus delta omega AC, delta BD plus delta omega BD equals eta CD. And to first order in delta omega, that implies that delta omega is antisymmetric.
Would you mind reading the indices in the line just above the one you just wrote?
This one? This one?
Correct, yes, that one.
Yeah. AB, AC, AC, BD, BD, CD. So that means that omega of lambda, which is omega of 1 plus delta omega alpha beta, is delta alpha beta plus delta omega AB times some matrix sigma AB alpha beta, where sigma AB is antisymmetric. It follows, and won't go through the calculation. I'll leave it as an exercise. The group law is obeyed. Then the sigmas obey an algebra that sigma AB, sigma CD equals 1/2 eta CB sigma AD minus eta CA sigma BD plus eta AB sigma CA minus eta dA sigma CB. And this is known as the Lorentz algebra.
What does it mean?
What does it mean?
Oh, saw that it's an implication of the group law and what's above, and we have this label for it. Actually, okay, so it's commutator relation between.
Yes. In algebra, you have some generator TA with TB is equal to the structure constant times TC. Lie algebra, that is. That's typically what a Lie algebra looks like, where these are constants that depend on what the algebra is. So you could have an SU2 algebra, you could have an SU3 algebra. The Lorentz algebra, as a matter of fact, is the group SO1, 3. So it would be SO4 if the space were Euclidean, but because it's Minkowskian, it's 1, 3. And that's the algebra. Those etas are the structure constants of that SO1, 3 algebra. So let's look at some examples. So each matrix that satisfies this algebra as a representation, we can look at some specific examples. Scalar, sigma is trivially 0. The Dirac field, and this is now the reason we're doing all this so we can explain fermions. This is a 4-component object, psi alpha. Alpha equal 1, 2, 3, 4. This is not to be confused with the space-time index mu, which is 0, 1, 2, 3. But alpha is the traditional symbol for spinor indices. Then sigma AB is a matrix which is 1/8 gamma A B alpha beta, where gamma mu alpha beta is the Dirac matrix. Have you met Dirac matrices? Anybody not met Dirac matrices? Okay. They're defined by gamma mu twice eta mu nu times the unit matrix. Now, why did Dirac invent matrices like this? It's because he wanted a relativistic equation for the electron, which we'll write down in a moment. Question?
It's not the anti-commutator term.
Oh, sorry. This equals, these curly brackets mean the sum. Thank you. The square brackets mean the minus sign. Curly brackets mean with the plus sign. Thank you.
When you wrote Dirac over there, should I interpret the word Dirac as meaning a mass field that obeys the Dirac equation?
Yes. Except, well, okay, fair question. It will turn out to be that, but at the moment, it's just a field that transforms according to a spinor representation of the Lorentz group. Now, that's the mathematics. The physics is that it obeys the Dirac equation, but we haven't made that step yet. Then there's a vector. And sigma AB now has CD indices, which make it delta AC eta BD minus delta CV eta AD. So, armed with this, we can now define Lorentz covariant derivatives. So we have some field phi alpha, which transforms as omega alpha beta phi beta. Could be anything. Could be scalar, spinor, vector. Look, d mu phi alpha does not transform as omega alpha beta d mu phi beta, because we're now allowing lambda to be a function of x, if you remember. So we have to, as should in a now familiar way, I hope, introduce a covariant derivative which does transform in a nice way. Where the covariant derivative, okay, some authors use different notations. We've used grad mu for a generally covariant derivative. So to distinguish it, I'm going to call that one d mu. Where d mu phi alpha is the ordinary derivative plus omega mu AB sigma AB alpha beta phi beta and in order, what is omega mu AB? Well, this is a new field. You remember in electromagnetism we needed an A mu field to form a covariant derivative. In gravity we needed the Christoffel symbol to form a covariant derivative. Now we've got a new field, omega mu AB, and in matrix language, omega has to transform like this. When phi transforms like this, so that the combination d mu plus omega mu transforms like this. Now an example is the Vierbein itself. The ordinary derivative of the Vierbein This is now a vector under Lorentz transformation. So it needs the ordinary derivative plus omega mu AB E mu B. That has a nice transformation property under Lorentz, but we still have to remember that it's a vector under general coordinate transformations as well. And so we can define something that is covariant under both as d mu A minus gamma lambda mu E A lambda. So this fellow is invariant under everything. It's invariant under general coordinate transformations, where E is a vector, and under local Lorentz transformations, where E is also a vector. Now, you remember in general relativity, this was not an arbitrary connection. It was related to the metric. And it's convenient to do the same for Vierbeins. We're going to insist that the covariant derivative of the Vierbein is equal to 0.
Excuse me? If a general coordinate transformation is any coordinate transformation, then how come the Lorentz transformation is not included in a general coordinate transformation?
Because, for example, as we've seen, the general coordinate transformations don't have spinors as representations. The Dirac field transforms as a scalar under general coordinate transformations, but it transforms as a spinor under local Lorentz transformations. So merely doing general coordinate transformations would be missing out on the fermionic nature of the fermion. And that applies to other fields that have indices that transform under the Lorentz group.
But I was thinking of a general coordinate transformation as really any coordinate transformation. Apparently I have the wrong impression. How should I narrow my definition or impression?
The local Lorentz group and the diffeomorphism group are different groups, and one is not contained in the other. And as an example, you can think of the Dirac field. The Dirac field transforms as a scalar under diffeomorphisms. Diffeomorphisms is another word for general coordinate transformations. But it transforms as a spinor under local Lorentz transformations. So it's not true that local Lorentz transformations are contained in the diffeomorphism group, because it has representations that the diffeomorphism group doesn't have. Now, we're going to insist that grad mu E mu A equals 0. And that allows us to solve, and again, I'll leave this as an exercise. You can solve for omega in terms of E. And it's a bit complicated, I suppose. we're only going to write it down once. There it is. The important thing to remember is that omega, and again, this is the difference between first order formalism and second order formalism. In this second order formalism, omega is a function of Vierbein. We could have a first order formalism in which E and omega are independent, like we did with G and gamma, and we may come back to that in a moment. Now, these covariant derivatives are based on important equations. Again, I won't derive them, I'll just quote them. Suppose we take the commutator of two covariant derivatives acting on this field phi alpha. We get R alpha beta mu nu phi beta, where R alpha mu nu beta is equal to R mu nu AB sigma AB alpha beta. So this is the Riemann tensor with two of its indices Lorentz and two of them were Einstein, dotted into a generator. That gives you a mu nu with alpha beta indices, and that's what sits on the right-hand side. And our suppressing alpha beta indices R mu nu, which is now not the Ricci tensor, but the alpha beta component of R alpha beta mu nu, is d mu omega nu minus d mu omega mu plus omega mu omega mu. If any of you are familiar with Yang-Mills, this is the same equation for the Yang-Mills field strength in terms of the Yang-Mills potential. So this is, to some extent, you can think of gravity as a Yang-Mills theory, where the Yang-Mills group is the Lorentz group. But there are differences as well as similarities.
I mean, the equation on the right hand for the last one, why there are two mu on the upper. The 1/2 EA mu.
Yeah. This one?
No, to the left. Yeah, that's one.
EA nu, EB sigma.
Is it
One should be
any mu be a B in the A mu?
AB mu sigma. Is there something wrong?
No, because it just write A mu and E mu sigma. It seems like to have two mu on the upper index. I don't know which is the right.
I'm sorry, I don't understand the problem.
So the second term is EA mu EB sigma. Is that right?
EA nu, EB sigma, yeah. Well, I was going to mention torsion, but since we're running out of time, I should probably move on to the fermions. So there's more we could say about that, but let's talk about the fermions in what time remains. So psi, the fermion we've decided transforms like this. This sigma is frequently used as an abbreviation for the commutator of two gamma matrices. So symbolically, psi goes like omega psi. To form an invariant Lagrangian, we want to have something that transforms like omega to the minus 1 psi. And I'm going to leave this as an exercise. To tell you that psi bar is the Hermitian conjugate of psi times gamma 0. So you can do that as an exercise. But the important thing is that there's a quantity psi bar that transforms in the opposite way to psi. So psi bar gamma A psi is a Lorentz vector. Psi bar psi is a Lorentz scalar. And psi bar sigma AB psi is a Lorentz tensor. So in flat space, the Dirac Lagrangian, which when you vary it gives you the Dirac equation, looks like I over 2 psi bar gamma mu d mu minus m psi. So in curved space, we have to replace the g's by etas, but we also need to make it a density of weight So we call this E for short. We need an E psi bar gamma A E mu A of x d mu minus m psi, where d mu was the covariant derivative we wrote down before.
Excuse me? Would you mind explaining where we want a density of weight 1? Do we have a density of weight -1 somewhere that we're trying to offset?
No, our action principle is d4xl, where L is the density of weight 1. So I'm just writing the Lagrangian. That guarantees when we integrate it d4x, we get an invariant quantity. Now, you can work out the energy momentum tensor, if you like. And to begin with, it comes with, if we vary with respect to E mu A, we get a tensor with 1 up, 1 Lorentz, and it looks like psi bar I E rho A E mu B gamma B d rho psi minus 1/2 E A mu psi bar I E rho B gamma B d rho minus m psi. I think there should be an I M there. So you can couple Einstein's theory to a fermion. Of course, you have to write Einstein's theory in terms of Vierbeins rather than in terms of metrics, which you can do. And this is how you couple fermions to gravity. So in order to do it, we needed all the apparatus of local Lorentz transformations, Vierbeins, omegas, and these omegas have a name. They're called spin connections. So to couple gravity to fermions, we need all the apparatus of Vierbeins, spin connections, local Lorentz transformations. And we have to make sure that our Lagrangian is invariant not only under Einstein's general coordinate transformations, but also under local Lorentz transformations. So let me finish by just giving you a glimpse of how this is used in supergravity. I'll just write down for you the supergravity Lagrangian without telling you all the heartbreak that went into finding it. Now, the Dirac field describes things like electrons and quarks, which are spin 1/2. But supersymmetry relates particles that differ by spin 1/2. So the superpartner of a photon would be a spin 1/2 fermion, but the superpartner of a graviton would be a spin 3/2 fermion. So supergravity, simple supergravity, is the theory of Einstein plus a spin 3/2 fermion. So it's a bit like the Dirac-Lagrangian, but a bit more complicated. So the Einstein part, and I'm putting 8 pi g equals 1, is just E times R of and there's two ways of doing it, first order formalism, second order formalism. The most elegant one turns out to be the first order formalism. So this is E and omega. And then we have our alternating symbol, epsilon mu, nu, rho. And the spin 1/2 fermion has a spinor index like an electron does, but it also has a vector index like a photon does, both. So we have psi bar lambda, and then there's something called gamma 5, which is the product of gamma 0, gamma 1, gamma 2, gamma 3. Gamma mu, d nu, psi rho. That's it. And it has a supersymmetry what's so novel about this when it was first found in the 1980s is that there's a symmetry that mixes up bosons and fermions. So the Vierbein transforms like this, where psi mu is a fermionic parameter. And delta psi mu transforms like d mu psi. So there's a theory of gravity that unifies bosons and fermions. And that's the simplest one. And I should tell you that if you look at the algebra, something interesting happens, because if you do a supersymmetry transformation twice, it turns into a general coordinate transformation. So in some hand-waving sense, supersymmetry is the square root of general relativity. And if Einstein had not already invented general relativity, supersymmetry would have forced us to invent it. Well, there's much more I could say about supersymmetry and supergravity, but time has run out, and we're getting squeezed because we just have one day left to talk about the history of the universe. So we'll do a brief history of time tomorrow. Any questions?
Then
in the Lagrangian particular space, the coupling with the spin connection and the fermion. That's essentially the manifestation of the coupling with gravity.
Yeah. You might ask, why don't I need the grad mu here? And the answer is it cancels out. It's just enough to put the ordinary d mu. Okay, see you tomorrow.